Okay, so hi, I'm Burke. I'm Christophe Pettus. I'm the CEO of PostgreSQL Experts, Inc. We're in Alameda, California. You can look at the slides will be up in about a week at thebuild.com, and my Twitter handle is XOF. I was an early adopter. And there's my email address. Okay, so there's so much stuff here. 1.7 introduced native migrations, but what we're specifically talking about today is 1.8 and 1.9 introduced and extended Django contrib Postgres, which is basically what we're talking about today. Lots of features, not much time, but we have to thank Mark Tamlin, who did most of the work on this and deserves the thanks of a grateful nation. Okay, the big stuff: array field, range field, HStore field, JSON field, array field. Okay. Arrays are first-class types in PostgreSQL, and array field allows you to use them directly. You can store an array as a single field in Postgres, and it's a very handy feature. They map into Python lists. You probably could have guessed that. Remember, PostgreSQL arrays are of homogeneous type. They're good old Fortran-style arrays. So they're integer arrays or they're character arrays or there's something like that. They're not. They can't be heterogeneous the way Python lists can be. So PostgreSQL multi-dimensional arrays are rectangular. I realize most people in the world were not born before languages discarded this as a bad idea, but the multi-dimensional arrays are rectangular. So it's 4 entries wide by 3 entries high. It's a grid. Individual entries can be null though, so you can kind of do ragged arrays that way. Once you have one of these, you can do queries on them. The basic one is contains. So it matches the field array on the left, contains all of the entries of the list on the right. So ABC contains AB, but you probably could have figured that out. And order is not important on contains. You have contains by, which basically goes the other way. Matches the list on the right with all the entries on the left. So ta-da, ta-da, ta-da. And order is not important here either. Overlaps works the way you'd probably expect. So ABC overlaps A and D, but ABC does not overlap D because they have no members in common. You also can take the length of it, which returns the length of the field on the left as an integer. So you can do queries like this, where you're querying for everything of length 2 or whatever you might want. Remember that unless, and we'll talk about indexing on these things because that's where things get really fun. Unless you create an expression index, you're going to do a full table scan. So it'll pick up every entry and rattle it, checking its length. We also have transforms, such as I want to find everything where the first element, the 0th element, is A. The one nice thing about this is if it's walking through this and you're saying find me the 12th element and there's an array field that only has 7 elements in it, it'll just say false. It won't return an error, so you don't have to write fancy trapping code for that. One downside is unless you use kwargs, you can't specify the index, the zero in this case, programmatically because it's baked into the parameter. Except for kwargs. You can also do slices. So find me everything where entry 0 or 1, match that. Or find everything where 0 or 2 contain this. So you can get arbitrarily complex expressions and really slow your database down. Unless you index them. Yay. So you just specify db index equals true and everything's solved, right? Wrong. This creates a btree index, which is pretty useless on array and other non-scalar types. So Postgres has lots of index types. Most people are only familiar with btree indexes because if you say db index equals true, which everyone does too much, stop it. Then what you get is a basic btree index. Btrees are nice. Interestingly enough, no one actually knows why they're called btrees. They're like balanced or Boeing or something like that. But they're kind of like a really good solution to the problem. They're fast, they're compact, and they provide total ordering. But they're not perfect because, first of all, btree indexes require a totally ordered type. And a points, an arrays, and HStore, total ordering doesn't make sense. I mean, 2 points, which one's greater than this point? I mean, you can make something up, but there's no intrinsic meaning to that. So, never fail. When in doubt, Postgres has your feature waiting for you. It'll do just and gin indexes. Gin indexes are used for types that contain keys and values, like arrays and HStore and JSONb. And GIST are for things that, this is my really big, I sound so smart, even though I'm the world's worst mathematician. GIST index is used for types that partition a mathematical space, like a point or a range or something like that. The nice part about them is once you create them, just like any index, they just work. If it can optimize a query, it will. You don't have to say, oh, by the way, on this query, use this index. So indexing array fields, generally you want a GIN index. And it accelerates contained by and overlaps. It doesn't help with links or slice, sorry. But you kind of have to use a raw SQL migration. Who's using raw SQL migrations? Everyone gratuitously put one into your next push, just to get familiar with them. You'll love them. They've always spoken well of you. So you throw in this fancy using GIN field clause. One downside of GIN things is they're not free to update. They're actually updated in a batch when you do a vacuum. And if that makes no sense at all to you, just ask me up the booth about that. So don't create one unless you need it. Specifically, if it's a small table, like an easy little mapping table, the whole thing's going to be in memory, so don't do this. But if it's a big table, do that. So you say, well, I was promised by an earlier slide that you would show me how to accelerate the search on the length field. That's how you accelerate the search on the length field. What you're doing there is saying, I want to create an index on the expression array length field, comma 1. The comma 1 is the dimension. So you're saying on the first dimension of this table. Remember Fortran? It's back. And you can index slice. You can also do slices. If, for example, this is something you do a lot, you can create one of these. Postgres is really smart, and when you use this expression in a query, it'll just find that index and use it. Just remember also, Postgres arrays are 1-based, not 0-based, like every other programming language, since, well, Postgres is from the 90s. It was different then. So why would you use array field? Well, if the underlying data actually is an array. Sometimes you want to put arrays in a database. They can be a replacement for a many-to-many table. If you want, we can chat later about how that, hallway track about how you might do that. You can also, and this is very common, use them as a denormalization if you have a really expensive query and you want to stuff that result in the database, and the result of it happens to be an array. Okay. Range fields. Range fields just are wonderful. They have native range types. They are about they span a range of a scalar type. I can read my own slides. For example, 1, 8 is an int4 range that includes 1 through 8. The brackets, the square brackets, mean inclusive. You can also do parens, which are exclusive, which means it only goes up through 7. That's really handy if it's like a float, or some infinitely divisible type. And that's the default. You can omit a bound to mean all values greater than or less than. So dates also have a special infinity value, which PsychoPG does everything it can to handle in a nice way, given that there's kind of this impedance mismatch between Postgres datetime and Python datetime. PsychoPG2, which is the interface library, if you're not familiar with it, includes a Python range-based type that handles all of that stuff for you. So you probably, when you're using it inside your application code, you want to import that and use that as your actual application type. 1.8, and thus 1.9, support integer range and big integer range, float range, datetime range, and date range. You can do contained by, and overlaps. They work pretty much the way you'd expect. You can also do fully less than, fully greater than, so if they're completely disjoint one way or the other, he said, gesturing wildly. And adjacent to means that they bump up against each other exactly. There are no values missing between them. And then not less than, not greater than, kind of work the way you expect. This is where you use a gist index. It looks just like the GIN index, only you say gist instead of GIN. And accelerates everything we've talked about. Woohoo! Goes really fast. And why would you use one of these? Well, here's a really hard problem. And we had no good solution for it until we had range types. So you're writing a booking system because people do things like that. And you say, don't allow 2 bookings to be inserted into the database for the same room where the dates overlap. Okay? You want a constraint that prevents that situation from arising in the database. With traditional unique constraints, there's no way of expressing that because you're not talking about a unique range because the ranges could overlap. but they're not equal, so they don't do that. But Postgres has a feature, because Postgres always has a feature, called Constraint Exclusion that will save you. Constraint Exclusion is a generalization of the idea of unique indexes, which basically it says don't allow two equal entries based on this set of comparison operators. So it's a generalization beyond equals. If these two things pass this comparison operator, which could be equals or it could be something else, into the table, like those could be overlap, for example. Now this is starting to sound pretty good. And you can, they can be any index-supported Boolean predicate, and they're all added together. So there's one catch, which has to be a single index. And range types require just indexes. So the index has to be a just index. But by default, the simple scalar values, like the room number, which was probably a character field or an integer, don't have just indexing. Oh dear, I lied to you. This feature won't work at all. Well, no, okay. There's an extension built into Postgres called btree gist that gives you all of those gist indexes for simple types like integer and character. It's a Postgres extension. It's part of contrib. You can use the create extension migration to get it for you. But it ships with Postgres, so you don't have to worry about it not being there on any installation. And just use the create extension migration operator and you're done. Okay, so how does this look? In your model, you say, I have a booking, and it's a character field, and the dates of the booking. Probably all you need to build a reservation system, right? Long weekend project, done. And so you run a migration, and that's what it looks like. You know, it has the usual integer sequence that we all love so much in Django, the room and the dates, and a primary key. But who cares about the primary key? We're not going to use that for this. And then you run this really exciting looking statement, which you are adding an exclusion constraint that says, don't let anything where the room is equal and the dates overlap be inserted into this database. Because at is the Postgres version of the overlap operator. Pretty neat looking. So people will be so impressed when you do stuff like this. So you create this booking, and you create a date range, and you save it. Say, well, okay, it's the first one in the database, so it better not, that better work, WAD. You create another one, but those dates don't overlap. They've checked out then. You create another one with the exact same time, but it's a different room, so that's fine. And now we're going to create a third one back on that room, except we're trying to check in before that guy's checked out, and then you get the blah, 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 blah stack trace integrity error, and it didn't let you do that. So you could catch that and produce an error or whatever. So why would you use range fields? Well, you probably want to use them to represent ranges. That's a good idea. They're more natural than the traditional high-low thing that we were stuck with before we had them. And you can do all this kind of cool database integrity checking on them. So they have HSOR fields. HSOR fields are boring. We're not going to talk about those because they have been. You can read about them if you want to, because we have the new hotness, which is JSON fields. They're new in 1.9, and they support arbitrary JSON structures. And they're stored as JSONb because Postgres has two different JSON types. And it supports the usual stuff, contains and contains by, both the key and the value have to match, has key, which finds JSON structures with a particular key, has keys, finds everything that matches a list, and all the good stuff, and has any keys. So, cool. You can do path type queries. You can say, find me the data is a JSON field, so find me data that has an object owner, that has a field name, whose value is Bob. Okay, that's cool. This is straight out of the docs. You can use array indexing if there's a JSON, if it's JSON. So data owner other pets, which is an array inside of the JSON structure, not a Postgres array, a JSON array. Number 0 has the name fishy. Remember I said there are two different JSON types. There's JSON and JSONb. JSON stores the raw text of the JSON, white space and all, exactly the way you put it in. It is, in fact, just a syntactic wrapper around the text type. JSONb is a compact indexable representation. It's like BSON, only much, much better. So why use JSON instead of JSONb? JSON's a little faster to insert since it doesn't have to do all this parsing fun. And there are two dubious features that some people, because JSON, started using in JSON, which are duplicate object keys at the same level, which is not supported in the spec, and stable object key order, where the idea being if you store a JSON field that has field A and field B, it'll always come out AB. There's nothing in the spec that requires this behavior. One thing to use JSON for is if you're just logging data and you don't really expect to do a lot of querying on it, it's faster to insert. Basically, everything else you want JSONb. And the biggest advantage is JSONb can be indexed in useful ways, unlike JSON. And the JSON field type gives you JSONb anyway, so just roll with it. Indexing JSON. So we use GIN indexing. Remember, this is for key value pair kind of stuff. It supports the has key has a single key. The path has a single key. Has any keys. Has all keys. You get it. One thing to remember is right now there's no single operator that's in Postgres that says find me this JSON field that has this key at any level in the structure. You have to look. You have to start at the top level and walk your way down, finding things. You can query them, but only in paths that are rooted at the top level. This isn't as big a restriction as you might think, but it is a restriction. So why would you use JSON? Well, if you're logging JSON data, like API calls, that's a good reason. You can use it for an audit table that works across schemas. This is a big problem in relational databases. You want an audit table that every time you change something, you spit a record into a table that says, I changed this. But that means, but what schema does that audit table have? It could mirror, you might have to, does that mean you have to create a separate audit table for every table you're in the database? That's pretty gross. Or, but with JSON, you can just turn the record into a JSON blob and store it right in. It's a friendly, readable way of pickling JSON objects that isn't, that doesn't have like infinite security problems like cpickle or YAML. And you can use it for attributes or rare fields. For example, you're building a system and you're going to deploy it, but your model is what it is, but you want the user to be able to create their own objects, like it's an inventory control system and they want to be able to create color or size or something like that. You can store them in JSON, so you don't have to modify the schema in the field. And there's other goodies. Most of these things have, everything has admin widgets that go with it, of course. The HStore and JSON widgets are kind of really only good for debugging because it's like gives you this text and burp and there you deal with it. And there's full text search. Now, full text search is a 1.10 features, which is in beta. Everyone download it and give it a go. PostgreSQL has had full text search built in for a long time. 1.10 finally contains model level support for it. First, you have to get some concepts down, and this is a little bit hard to wrap your brain around. I have to go back to the docs sometimes on this. There's this thing called a TS vector, which is a block of text. You can think of it like the blog entry or the description in a catalog or something like that. Big old block of text encoded for full text search. So transformations have been done on it to normalize it, strip all the uninteresting extensions out, remove the stop words, all that stuff. It's a built-in Postgres type. Doing that transformation requires this thing called a configuration, which I am not going to go into because we could have spent the entire time. So, am I out? Okay. I'm going to plow through because I want to get through this. Postgres has a bunch of configurations. Generally, just use those. Like English is the standard one. Just use it. ToTS vector is a function built into Postgres that takes text and returns a TX vector like that. Fortunately, you don't have to worry too much about this. Django calls this under the hood for most situations. And then you have a search functionality. So you can search a text field using full text searching using the __ search predicate in a query set. Without indexes, it does a sequential scan, which is bad. So you don't want to do that. You can, there's a search vector object at the top level in Django that represents a TS vector. It lets you search more than one field at a time by combining them. Merging and searching happens as the query runs. Search query represents a query object, does the stemming and things like that. So you can do searches like that. Cool. PostgreSQL also has ranking, so you can sort things in relevancy order and blah, blah, blah. There's lots more. These slides will be online. The important thing to remember is you need an index, which is a GIN index, in order to make this work fast. You can combine multiple fields with different weights and all this kind of stuff. Generally, you need to use a trigger to do that kind of stuff. There's examples in the documentation on how to do that. And there's 3 things which you can read about in the docs, which are relatively small features. Questions? No. And if you didn't understand any of that, hire us. And thank you.